Hello everyone, today we're going to look at the next section, and this is on proofs. So there are different types of proofs, and we're going to look at two different types of proofs today. The first one is called disproof by counterexample. So when we're trying to do proofs, it is actually quite difficult to prove that something is always true by looking at the examples. However, it is possible to use examples to prove that something is not always true, and this is called a counterexample. So let's very quickly have a look at the first question. Disprove by counterexample that x plus 1 squared equals to x squared plus 1 for all x. So we are trying to find an example to show that this is not true. Okay, so you can pick any number you want, but we tend to start picking some nice numbers. For example, 0, 1, and 2. So let's say if I do pick x equals 0 and I put into the bracket, and the result on the left-hand side will just be 1 squared, which is 1. And on the right-hand side, it will also be 1. So that means I don't really want to pick x equals 0 as my counterexample. So I might use a different number. So let's say when x equals to 1. And we always have to split it to look at the left-hand side and the right-hand side separately and then compare them. So let's substitute x equals 1 to the left-hand side. We'll get 1 plus 1 squared, which is 2 squared, and that is 4. Right-hand side will now equals to 1 squared plus 1, so that is 1 plus 1, that equals 2. And then we notice that our left-hand side does not equals to my right-hand side. So now we have disproved it by using a counterexample. So then we can say our x equals 1 is a counterexample. Okay, let's look at another one. So for this question, when you disprove the following statement by finding a counterexample, and the statement says that for any pair of integers x and y, if x is greater than y, then x squared plus x must be greater than y squared plus y. Okay, so it's perhaps quite obvious that if I pick both of my x and y to be positive numbers, then this inequality will have to be true. However, we are going to consider some special cases where perhaps one of them is positive and the other one is negative. So let's do that. So let's say when x equals to, let's say x equals to 1 and y equals 2, let's go for minus 3. So let's substitute into our left-hand side. So left-hand side now equals to 1 squared plus 1, which is 2. And the right-hand side now equals to y squared, so it'll be minus 3 bracket squared plus a minus 3. So that will be 9 minus 3, which is actually 6. So now you can see that my left-hand side equals 2, right-hand side is 6, and actually 2 is smaller than 6. So that means the left-hand side has to be smaller than the right-hand side, which means the statement is not true. So that means my x equals 1 and y equals minus 3 is a counterexample. Okay? Right, so now you should spend some time and then go through the questions in exercise 1C. Okay, now we're going to move on to the next type of proof, which is called proof by deduction. And all it means is that we're going to use some logical steps and some algebraic manipulations to prove the statement is true. And in GCSE, you have already come across this type of proof, and in GCSE, we'll actually call it proof in GCSE, we actually call it algebraic proof. Okay. Now, we know that from GCSE, we can always use 2n to represent an even number and 2n plus 1 to represent an odd number. But of course, I can continue. There's many of them. I could find the next odd number, which will be 2n plus 3, or perhaps the one before 2n plus 1, so that'll be 2n minus 1. So you can always change them into different versions depending on the question. Okay, so let's have a look at the first example. Prove that the product of the even and an odd number is always even. So let's decide what is my even number and what is my odd number. So let's just go for 2n is my even number and 2n plus 1 is my odd number. Product means I want to multiply them. So let's do 2n times by bracket 2n plus 1. So that equals to 4n squared plus 2n. It looks quite obvious that the final result must be an even number. However, when we do proof, we must show another step. So if we're asking for even, that means we have to write it as a multiple of 2. So I need to factorize the 2 out. The n doesn't matter that much in this case, but the 2 is the key thing. So factorize the 2 out, and inside the bracket, we'll end up with 2n squared plus n. So now we have written this as a multiple of 2, so that means it must be even. Okay, or you can even continue here, say that will equals to 2k when k actually equals to 2n squared plus n. Okay, so basically you want to write your final result in the form they're asking to get. Okay, let's look at another one. Prove that the difference between the squares of consecutive odd numbers is always a multiple of 8. So consecutive means one after another one, and we want odd numbers. So I'm going to pick 2n minus 1 and 2n plus 1. Of course, you can go for 2n plus 1 and 2n plus 3. The reason why I didn't go for that is because I saw that I have to square them. So I'm kind of hoping that perhaps something will cancel out if I have a minus 1 plus 1. Okay, but of course you can use a different odd number if you want. Okay, so now, firstly, I need to write down. So we're looking for the difference, which means I want to subtract. And it's the difference between the squares of the consecutive odd number. So then I have to go for the bigger one, 2n plus 1 squared, minus the smaller one, 2n minus 1 squared. Okay, so what we can do here is that I could, of course, expand those two brackets, but instead of doing that, I mean, it's fine, but it will take us a little bit longer. So instead, I'm going to use the difference between square formula. So a squared minus b squared equals to a plus b times by a minus b. And straight away, you can see what is a and what is b. So that would be a. So your a will equal to 2n plus 1, and your b will equal to 2n minus 1. So let's put into the formula. So we have a plus b, so we 2n plus 1 plus 2n minus 1 times by a minus b. So 2n plus 1 minus, now be careful with the sign, so I want to take away 2n and take away a negative 1, which means I have to switch it to a plus 1. So you can see I do have a few things I can cancel out, so I have a plus 1 minus 1 and cancels out, and I end up with 2n plus 2n, that's 4n. Then I will have 2n, take away 2n, cancels out, 1 plus 1 equals to 2. So finally, I have 8n, and it's already written as a multiple of 8, so I don't do that final step. So that by showing that, now I have proved this statement. Right, let's look at another one. Now, this one is always a slightly tricky one that confuses the student. So here we had to prove that x squared plus 4x plus 5 is positive for all values of x. How can something be positive? Well, we can always link back to something else we've done GCSE, or actually at the beginning of this year. So anything squared is always positive or 0. And here I have a quadratic expression, so perhaps we can start by completing the square. So my x squared plus 4x plus 5, I can change it into x plus 2 squared minus 2 squared plus 5. And that equals to x plus 2 squared minus 4 plus 5, which can be simplified to x plus 2 squared plus 1. Okay, so how can I show that this is always positive? So if I want to show something is always positive, I want to show that it's bigger than 0. Okay, so then I would start to look at this completing square part. So the first thing I'll write down is I'll say my x plus 2 squared is always greater or equals to 0. And that is true because anything squared has to be greater or equal to 0. And then I want to make it look like the final expression I have. So here I have a plus 1 at the end. So I'm going to plus 1 on both sides of my inequality. So now I end up with x plus 2 squared plus 1 has to be greater or equals to 1. So now you can see that my left-hand side of the inequality looks exactly the same as the expression I have now. However, here it says on the right-hand side that this expression has to be greater or equals to 1, but we said we just wanted to be positive, so greater than 0. So now you can think, if something is always greater or equal to 1, then of course that will always be greater than 0, but obviously not include 0. Okay, so then I can say that this must be true for that. And now I have proved it by using an inequality. Okay, now, so I'm going to give you some time so you can now complete exercise 1D in your book, please.